Greetings students, today I'm going to evaluate an integral for you as the integral from 0 to infinity of x times natural log of x divided by x cubed plus 1. One way to evaluate this interesting integral is to use counter integration. However, I'm going to use Feynman's technique of integration and a representation of beta function to evaluate this integral for you. So I'm going to define I as a function of parameter alpha as the integral from 0 to infinity of x to the alpha divided by x cubed plus 1 dx. And if I differentiate this I with respect to the parameter alpha, I get the integral from 0 to infinity of x to the alpha times natural log of x divided by x cubed plus 1. And it's easy to notice that our goal integral I is actually I prime evaluated at alpha equal to 1. The representation of beta function that I'm going to use is beta as a function of the parameters u comma v as the integral from 0 to infinity of t raised to the u minus 1 divided by t plus 1 raised to the u plus v integrated with respect to t. And we know that beta function is defined as gamma of u multiplied by gamma of v divided by gamma of the summation of u and v. To turn that I of alpha into a form which resembles beta function, I have to use the substitution of x cubed equal to t, or x equal to t to the third. The bounds of integration would remain unchanged from 0 to infinity, and we get dx as a third times t to the negative 2/3 dt. So now I can write that I of alpha as a t integral equal to, I'm going to pull that third out, and then the integral from 0 to infinity, we have x to the alpha, which is t to the alpha third, times dx, t to the negative 2/3 dt, all over x cubed plus 1, which is t plus 1. And if I combine the exponents of t, we get 1/3 times the integral from 0 to infinity of t raised to the alpha minus 2 over 3 divided by t plus 1 dt. Now if you compare this integral with the representation of beta function, you notice that u minus 1 is alpha minus 2 divided by 3, and u plus v is equal to 1. So we have u minus 1 equals to alpha minus 2 over 3, and this yields u as alpha plus 1 over 3. And since u plus v is equal to 1, we can actually get a nicer representation for this special case for the beta function. We get beta of u comma v equals to gamma of u times gamma of v divided by gamma of 1, which is 0 factorial, or 1. And since u plus v is equal to 1, I can write this as gamma of u times gamma of 1 minus u. And then using the Euler's reflection formula for the gamma function, we can write this as pi times cosecant of pi u. So finally, I can write I of alpha as 1 over 3 times pi times cosecant of pi u, where u is alpha plus 1 over 3. Remember, our goal integral is I prime evaluated at 1. So I'm going to differentiate this I with respect to alpha. Get I prime of alpha as pi third. The derivative of cosecant is negative cosecant times cotangent. So I get a negative sign out, and then cosecant of pi third times alpha plus 1 times cotangent of pi thirds alpha plus 1 multiplied by the derivative of the inner function from the chain rule, so we get another factor of pi over 3. And finally, our I, which is I prime evaluated at 1, is equal to, combining those two pi over 3, we get negative pi squared over 9 times cosecant of pi third times 1 plus 1, so that's 2 pi thirds, multiplied by cotangent of same argument, 2 pi thirds. Cosecant is 1 over sine and cotangent is 1 over tangent. So this is negative pi squared over 9 times 1 over sine of 2 pi thirds times 1 over tangent of 2 pi thirds. Sine of 2 pi thirds is same as sine of pi thirds, or 60 degrees. So square root of 3 over 2. And tangent of 2 pi thirds is negative tangent of 60 degrees, or negative square root of 3. So finally we get positive pi squared over 9 times 1 over root 3 over 2 times 1 over root 3. And after rearranging and simplification, we finally get 2 pi squared over 27, which is the final answer. And that's a good place to stop. Thank you so much, and see you next time.